A storm, from a meteorological perspective, is understood as a set of electrical, optical, and acoustic phenomena occurring between cumulonimbus clouds themselves or between these clouds and the Earth's surface. A storm is therefore defined by the presence of lightning. Any heavy shower is considered a storm only if lightning activity is detected. Storms are observed in cumulonimbus clouds. These are massive towering clouds with significant vertical extent. The highest parts of a thunderstorm cloud in our latitudes can reach heights of around 15 kilometers. A cumulonimbus storm cloud forms under suitable conditions gradually from a cumulus-humulus cloud, through cumulus mediocris and cumulus congestus stages. While the developmental stages of the cumulus cloud resemble cauliflower with sharply defined edges, the cumulonimbus spreads out at the top, and its structure becomes fibrous or fan-shaped. This part of the cloud is called the anvil and is a typical feature of the upper part of the cumulonimbus cloud, visible even to the naked eye. The thunderstorm cloud spreads out at the top of the troposphere because updrafts hit the tropopause. To explain the formation and forecast of storms, the ingredient method is used. Only 3 ingredients are needed for a storm to develop, but if even one is missing, the storm will not occur. For storm development, a sufficient decrease in air temperature with altitude is needed, which is called the vertical temperature gradient. The air must be unstable, meaning it is not stable. If, in such a case, an air parcel is displaced, for example upward, it will continue this movement and accelerate. We distinguish between conditional and absolute instability. Conditional instability occurs when the vertical temperature gradient lies between the saturated adiabatic and dry adiabatic lapse rates. The dry adiabatic lapse rate is practically 1 degree Celsius per 100 meters, and the saturated adiabatic lapse rate varies depending on temperature and air pressure. At 0 degrees Celsius and 1000 HPA air pressure, it is approximately 0.6 degrees Celsius per 100 meters. This value is generally considered in our region. Another important parameter is sufficient air humidity. Here I mean absolute humidity, not relative humidity. At the end of autumn and in winter, the air may feel humid, but the total amount of water vapor is less than in summer when the air is warmer. The last important parameter is initialization, an impulse that forces an air parcel to rise. This impulse can be, for example, a cold front. To explain the development of a thunderstorm cloud, the particle or bubble method is used. Imagine the air as bubbles like those forming in boiling water. Not all parts of the Earth's surface heat equally, and over some areas, these bubbles of air are warmer and rise due to buoyancy since warmer air is less dense. This phenomenon is called convection, that is, upward and downward air movements. We have introduced many technical terms, but we still might not be able to imagine how a storm forms. Picture a typical sunny summer day with an air temperature around 30 degrees Celsius. Late in the afternoon, a cold front arrives in our region. The temperature decrease with altitude near the surface is steep, approaching 1 degree Celsius per 100 meters. Higher up, it is slightly lower, around 0.7 degrees Celsius per 100 meters. Several hours before the front arrives, no clouds form because the air bubbles do not feel like rising. Although some try to move upward, they lack a strong impulse. Once the cold front moves over our area, the cold air pushes into the warm air like a wedge. At the boundary between warm and cold air, the warmer air slides over the denser cold air and reaches higher parts of the troposphere. The air bubbles initially cool according to the dry adiabatic lapse rate because the air inside them is not saturated. Once cooled to the dew point, water vapor condenses, releasing latent heat, and the bubbles or air parcels then cool only at about 0.6 degrees Celsius per 100 meters. If you haven't lost track yet, this is the saturated adiabatic lapse rate. We said that the vertical temperature gradient of the surrounding air is 0.7 degrees Celsius per 100 meters. This means that above the condensation level, the air parcel is always warmer than the surrounding air, which cools slightly faster with height. This is the driving force for thunderstorm cloud development. The parcel is propelled by buoyancy and accelerates until it reaches a layer where the surrounding air no longer cools with height but warms. Under ideal conditions, it rises until it hits the tropopause. This entire process can also be graphically depicted, and the work done by the buoyant force, required to lift the parcel can be calculated. The result is the Cape Index. This parameter is used to forecast storms and indicates how intense storms might be if they form. It represents energy that may or may not be released, because to use this energy, the parcel must reach the level of free convection. This is the altitude at which the temperature of the rising parcel equals the temperature of the surroundings, and above this height, the parcel is warmer and can accelerate upward toward the tropopause. This concept is simplified, as many things in meteorology are, because actual atmospheric processes are more complex. For example, it assumes the air bubble we have been discussing is isolated from the surrounding air, which is not true. You might not know it, but this lesson also explains why there are fewer storms in winter than in summer and why storms don't form just from heat. In winter, the air is drier and its layering is often stable, not unstable. Temperature inversions are often observed, where air warms with height rather than cools. This is the worst environment for storms. In summer, there is more moisture in the air, and near the ground, it is warm due to strong sunlight. However, it must also be relatively cooler at higher altitudes. Otherwise, it won't work. So heat alone is not an ingredient for storms. Just imagine how hot it is in the Sahara and how many storms they get there. I know this lesson was complicated, but that's the world around us. I hope this didn't discourage you and that you support this content by subscribing. If you have any questions, leave them in the comments and become part of the biggest community of weather enthusiasts in the world.